Okay. So who else are missing today? I think Chandramani anyway dropped off. Uh, anyone else? Savan?
Ayush,
Ayush is
no.
also there. Yeah. Only Ayush? Okay. Okay. So you guys can see the screen, right?
Yes, sir.
Okay. So now let me just do a quick recap of what we did in the last few lectures. We looked at an important theorem, rather a lemma called theorem called Borel-Cantelli. It's actually Borel-Cantelli lemma, right? So what is Borel-Cantelli lemma? There are two parts to it. The first part says if you take events A1, A2, etc., right, with summation over all I probability of AI less than infinity, then probability of AI occurring infinitely often is 0, right?
Zero.
This is the first part. The second part is AI, that is A1, A2, etc., independent, and if you look at summation over all I probability of AI is infinity, implies probability of AI or AJ occurring infinitely often is 1,
One.
right? Is that fine? Okay, so let's break open some of these. Let's take the second part. Okay, so what do you mean by probability of AI occurring AJ occurring infinitely often? Can somebody tell me? Hmm?
So we
Yes.
can write it in intersection and union of
What
AI.
does that mean? That mean what
So
is
like
what
after,
is the meaning of AJ infinitely often?
so it's like after a point n, it can happen in n plus one or maybe n plus two and maybe n plus three, and we are taking the intersection of those unions.
Correct, right? So essentially, you are saying A1 or A2 or and so on should occur, right? And A2 or A3 or and so on should occur, and so on, right? So it's essentially you have to take the union, let's say from J equal to M to infinity, AJ. So this should happen for every M, right? That's what it says. So overall, M equal to 1 to infinity, right? This is what this is saying, right? Now let's look at this this particular the result second two, right? AI is being independent and the sum being equal to infinity implies AJ infinitely often equal to 1. Suppose this is true, that is AIs are independent, and let's see what are the consequences, right? So let's look at what is it that this is saying. So let's take events. Let's look at random variables now. So x1, x2, etc. Let's assume IID. Okay. Now suppose I say that xn converges to x almost surely. What does that mean? What does that mean? Can somebody tell me what is the meaning of this?
So probability of xn tending to x
Huh.
is equal
Is
to 1.
1, right? Or the measure of this event is 1, right? So I can break open this. So we wrote it in terms of intersections and unions. What was that? It's for every epsilon there exists an n such that for
Depending.
every n greater than or equal to this, right? So
Yes.
what is it that that particular thing is saying? So intersect. So it's for every
Intersection point.
epsilon or for every k, right, equal to 1 to infinity. There exists an n, right? Nk
Yes.
equal to 1 to infinity, such that for every n from nk plus 1 to infinity, right? This ax n minus x, right, is less than k
1
1 by k, This is 1, right? This is what it says, right? Do you agree?
Yes.
Okay. So now, what can you say about this now? So 1 is equal to probability of intersection. Suppose I leave out intersection, what do I get? I get this, right? If I leave out this intersection for every k, right? It essentially means that 1 equal to this. Do you agree?
Yes, sir.
Hmm? Do you agree with this? So, what I'm trying to do is relate this with Borel-Cantelli. Okay, so what does Borel-Cantelli essentially means, right? So, I'm trying to prove that, for example, if AIs are, let's say, AIs correspond to, let's say, xi minus x less than epsilon. Okay, okay. Let me write it like that. Okay, so let me write it like that. Now suppose AIs or AI, I'll define it as, okay, let's look at this thing, okay, is less than epsilon, okay, is that fine? So this is the event, so xi minus x less than epsilon, or let's look at the reverse, bad event, okay, this is the bad event, okay. Now, suppose, let's also say that summation over all I, probability of AI is less than infinity. So, what can you infer from this? Suppose I tell you this, what does that mean?
AI occurs finitely many times.
Hmm?
AI occurs only finitely many times. Or it occurs infinitely many times with probability 0.
Yeah, so this essentially means what? Probability that AI occurring infinitely often is 0, right? So what does that mean? What does that mean? Hmm? What does that mean?
I mean, xi will
So
converge to x.
So
Hmm?
AI will occur finitely many times.
No, AI infinitely often is 0. That means this event, right? This thing, this kind of thing, is 0. The complement of this. I mean, instead of less than 1 by k, it will be greater than 1 by k, right? That will be 0. That's what it says, right? Of course, you have to replace it by this by epsilon, right? That's what it says. So now the question is, can you relate, given this, can you relate almost sure and Borel-Cantelli? Okay. Okay, so this I will leave it as a homework. So take this as an assignment. So for example, the hint is you should be able to write events as some bad event or good events. And based on that, you should be able to say, for example, use one of the Borel to conclude that if, for example, this happens, xi converges to x almost surely. Something like that. Is that fine? Okay. Try that. If you don't get it, just ping me. We will look at the proof of this, or at least I'll give you more hints on how to go about it. Okay. Okay. So I thought before going into stochastic processes, later we will need some notions like dominated convergence theorem and all that. Maybe a few theorems along those directions are very essential. So what I will do now is, so this class will be slightly different. So I'll ask you to figure out or tell me what to do next. Okay. So the first result, I'll call it as a theorem, is the following. Suppose, let's say, suppose xn converges to x in probability, then there exists a subsequence let's say x and m, that converges to x almost surely. See, now you know the fact that if xn converges to x almost surely implies xn converges to x in probability. But the other way is not true. But what this says is there is a subsequence that converges. Now, how do you solve this? How do you prove this? Yes. Okay. Now let me also give you a hint. Okay. So hint or a result that you can use. Okay. Okay. So suppose let's say if summation or all I probability of mod of xi minus x greater than epsilon is less than infinity. Okay. This essentially implies what? Well, Borel-Cantelli says that this implies mod of xi minus x greater than epsilon occurring infinitely often is 0. So this essentially implies that xn converges to x almost surely. Okay. So this is the result that you will prove as a part of homework. But now supposing you know this result, now, yeah, this is correct. This is true for every epsilon. Okay. So now, how do you use this result to prove the theorem? Can you think of how to prove this with this particular hint or result? Yes. What would be the first step?
Should we divide xn into smaller subsequences and then
meaning?
So I mean xnm is a subsequence of xn, so there must be if we eliminate xnm from xn, there must be some non-negative subsequences in xn. From that, some probability or inequality.
Okay, so let me write this. Okay, so what is xn converging to x in probability means? This means, or this is the meaning of this is limit n tending to infinity probability of xn minus x greater than epsilon, or let's say instead of epsilon I'll write 1 by m. This is 0 for all m, right? This is what it says. This is the definition of xn converging to x in probability. So what can you say about this? If probability of a bad event is 0 in the limit, right? Remember, probability is a sequence of deterministic numbers, right? It's a usual sequence. Now I'm saying limit of that sequence is 0. What do you mean by that? Say, remember, I need to essentially show this, right? I need to show something like this: summation of some probability less than infinity. Therefore, xn implies xn converges to x almost surely, right?
So we can find some way that every possible event, if probability is 0 or something finite, then we can tell that.
No. So okay. So now let me give you another idea. Okay. So from the above meaning the limit n tending to infinity probability of whatever that greater than 1 by m equal to 0, that implies there exists n1, okay, such that probability of xn1, let me use n1 minus x greater than 1 by m is less than half. Do you agree? I can always find such an n1 because in the limit, if it goes down to 0, then I can find a small room of size half so that the sequence will remain inside that room forever, right? So that stage is n1. Is this fine?
Yes, sir.
Do you agree?
But sir, how can we say that the probability of that event will be less than half? We can find this
Because
n1 so that this event will follow. But how can you tell about their probability, like event probability of this event, sir?
okay, so let me give you a, so suppose I say that an converges to 0, okay?
Yes, yes, sir.
That means if you look at a1, a2, etc.,
Yes, sir.
somewhere down the line there should be an1
Mhm.
after this, including an1, right?
Yes, sir. Yes, sir.
So this should be half close to 0. Do you agree? If we cannot find such a number, if it is not at least half close, then it doesn't, it essentially contradicts the fact that an converges to 0, right?
Yes. Half.
Do you agree? So 0 is here, right? If a sequence converges to 0, that means if you put a room which is of size half, eventually the sequence should enter that room and be there forever, right? It cannot come out, right?
Yes. Mhm.
That means I can find at least n1 such that this
Yeah, sir.
an1
We are
is,
able to find this thing, but like here, 1 by m is given, no? So greater than 1 by m. So, but their probability is less than 1 by 2. I'm not
okay,
getting that.
fine. So give me any epsilon, I can find any m, right? 1 over m. I can always find an n1
So,
such that this
yes,
is less
yes,
than
sir, I
half.
got it, sir. Actually, we are taking the limit over these probabilities. Yes, sir, I got it, sir. We can
No,
do
yeah.
so.
So the limit is over n, right? This side,
Yeah,
not n. Okay.
means that this probability of each event will give a number, then we are taking the limit on that
Yeah.
numbers. So,
Yes.
yes, sir, we can find then, yeah.
Yeah. So let's, for a moment, let's fix this m. Okay. So let's not worry about m. So give me any m, I can find this, right?
Yes,
Okay. Is this fine?
yes,
Everyone? Right? So similarly, by induction, there exists an n2 in n such that n2 is greater than n1 and probability of xn2 minus x greater than 1 by m is less than 1 by 4.
1 over 2 square.
Okay. Can you continue? Can you complete the proof now?
Yes, sir, yes, sir.
What is it that you have to do next?
Sir, in the same way, we will get this less than equal to 2 to the power something n.
Yeah. And so
And
on. There exists an nk, okay, greater than nk minus 1, greater than, and so on, greater than n1, such that, right, probability of x nk minus x greater than 1 by m is less than 1 by 2 to the k,
or n.
right? This is
Yes.
what I can prove. Okay. Now, can you
Hello,
complete
sir.
the proof? Yes.
Sir, is it like we are fixing m and then we are
Exactly.
finding the n1 and
Exactly.
n2 for that the
Yeah.
sequence will be probability will be less than 1 by 2,
Exactly.
1 by 4. Okay.
Exactly. Exactly. So
Now
you
the
are
summation is less than infinity, and so from that we can conclude.
exactly right. So you are done. So this
Yes.
implies what? Summation overall k equal to 1 to infinity, probability of x and k minus x greater than 1 by m is nothing but, or it's less than summation overall k equal to 1 to infinity 1 by 2 power k, which is less than infinity, implies x and k converges to x almost surely.
Surely, yes, sir.
Right? The nice result, right?
Yes.
Now,
Sir,
this is true for every m, right? So you give me any m, I can choose a different sequence. Yes.
So that is it necessary to fix the value of m for that, for finding 1 by 2 power k, or we can do?
Not really. So what I'm saying is, you give me any m, I can do this. So that means it's true for any m. For any m, I can do this, right? So that completes the proof. Essentially says that x and k converges to x almost surely, because this whole sum, right? This is less than infinity for every m, right? In fact, I should write for every m, right?
In fact, sir, this probability we are taking 1 by 2 to the power k. In the same way, we can choose any number like 3 to
Yeah,
the power k type, 4 to the power k type. No, sir.
yeah.
Yeah, our target is to make this finite only.
Finite. That's all. That's
Okay,
all.
sir.
Yeah. So is this proof okay? I mean, fine, right?
So, can you go to the statement once again? Statement. Yes, sir. So here you have mentioned like there should here you have mentioned that then at least a subsequence xn of m converges to like
X almost surely. Yeah.
Sir, like every subsequence should converge, or
No,
if any one is
Obviously
there,
not,
then
right?
it's okay.
No. I'm at least there exists one subsequence that converge. At least one. Okay. Is that fine? Because every subsequence converges, then I can say that xn converges to x almost surely, right?
Yeah. Oh, yeah.
Right? So that is not true. We gave a counter example in one of the classes, right? The dyadic pulse moving back and forth with the width shrinking, right? That converged to 0 in probability, but did not converge to 0 in almost sure sense, right? So that's a counter example for this thing. So xn, just keep in mind, xn converges to x in probability implies there is a subsequence such that x and k converges to x almost sure.
Hello,
Okay?
sir.
Yes.
So to prove this, sir, why did we use the improbability convergence statement?
Okay. Exactly here, right? This thing. This is the definition of improbability convergence. So if I say that limit of some sequence goes to 0, that means there is a stage beyond which, that is n1, beyond which it should be less than half. There is a stage n2 beyond which it's less than 1 by 4. There's a stage beyond which it's less than something like this, right? This is half, and then there is a stage.
Yes.
Yeah, there is a stage which is like 1 by 4, and it stays there, and so on, right? That's the definition of limit. How many of you know what is the definition of a limit? Yes, Jayant? Jayant, are you there?
Hello, sir. Yeah.
Yes. Do you know the definition of limit?
Means, sir, if let's say x there is some sequence, sir, x. Hello.
Okay.
X such that it's within some x plus or minus delta within that range. Then f of x.
No, right? Limit has got nothing to do with functions, and moreover, x is not a sequence, right? It's a number. Xn, n being natural or countable, is a sequence. Okay, Praveen, can you tell me what is the definition of of convergence?
Sir, let's take a sequence an.
Hmm?
So there exists some band. Once an enters that band, it never leaves, like that.
Okay, that is fine. That is intuition, right? So can you precisely define? So Ayush, can you tell me?
So I would also tell the same what Praveen said.
Okay. Who else? Rishabh?
So is it like if an is a sequence, then there is a limit n tends to infinity that an minus a is mod of that less than equal to some epsilon, where epsilon is very
No, I
small
don't
number.
see. What you have to do is you have to convert your intuition into math, right? So we say that n converges to a if you take any room, right? if for every epsilon greater than 0, epsilon is your room, right? If you take any room, there exists a stage, right? There exists a n epsilon belonging to n, such that if you look at the sequence beyond this stage, that sequence will be inside the room, right? It says that for every n greater than or equal to this stage, x an minus a will be less than epsilon. This is the definition. Okay, keep in mind this definition. So this is any room. Okay, maybe I'll write it.
So that means epsilon can be a big number also.
Yeah, it should be any room, right? Big
Then
number
how
is
can we
always
say it is
a problem.
convergence? Convergence, we intuitively we think that it's almost same or something like that. The values are.
No, that's why I'm saying it's for every room, right? Every means you can make it really, really small or you can make it really, really big. Doesn't matter. It should be true for everything, right? Small and big are relative, right? So that way it's for every epsilon. You give me any small room or big room, whatever. If you take a big room, then the stage would be very early, right? The sequence will enter that stage very early, or it would have already entered. See, if you take an epsilon to be infinity, right, then it's already there. I mean, every sequence is inside that infinity room. If you take a room of half, then maybe after 1000, it will enter that room. If you take a room of 0.0001, after 1 billion, it will enter that room and stay there. Okay?
Okay, sir. Okay.
This is the stage. Okay? Any room, and this is the stage. Such that for every n beyond the stage, okay? This is your beyond the stage. Such that, what is this saying? This is saying sequence remains inside the room. Okay? Is this fine? Everyone okay with this?
Yes, sir.
Okay, so let's look at one more. This is, again, I will ask you to think about this and prove. Maybe a problem. Okay, so let you take a positive or a non-negative random variable, be a random variable. Okay, then expected value of x equal to limit n tending to infinity, expected value of x n. Okay, I'll tell you what this is. This essentially is minimum of x comma n. Okay, fine. This is the definition. Very intuitive, but how do you prove this? How do you prove this?
Sir, is x is a sequence? I mean.
No, x is a random variable, right?
Yeah, x is a random variable.
Think of it as Gaussian, right? I'm taking minimum of x comma n. So practically, how do you think of it? Essentially, what you are trying to do here is, for example, n is 500, right? So what you are trying to do is you are trying to sample from Gaussian, let's say zero mean unit variance, some 100,000 samples. Whenever that sample crosses n, that is 500, you take it as 500. Otherwise, you take the sample as is. You get 100 billion samples. Just average it. That will be the right hand side. That is expected value of x caret n, right? The left hand side is expected value of x, which is 0. So what it's saying is it's limit. The only thing is Gaussian is both. It's not non-negative, but x in this case will be non-negative. So what do you do now? How do you solve this? Okay, let me ask you the first one. Okay, suppose probability of x less than some n is 1. Now how do you show this? Can somebody finish the proof quickly for this case? Yes. Can somebody tell me? Yes, I'm waiting. Somebody should speak. So, Praveen, did you understand what is the problem?
Yes, sir.
Ayush,
Yes, sir.
does it make intuitive sense? See, think of n equal to infinity, right? So what will happen? So you're saying minimum of x comma infinity, that is x itself, right? Intuitively it makes sense, but how do you prove that? Jayant?
Sir,
Yes,
sir, can you go to the screen?
Yeah.
Sir, we are assuming that probability of x less than n is 1. So that
suppose that is true.
Yeah. What this means is if x is greater than n, it's 0.
Correct. Probability
So
is zero.
minimum. So minimum of x comma, let's say capital N. That
see,
this is basically definition of a CDF. Am I right? Probability of x less than n, and if I take n tends to infinity, that gives the probability f of infinity, capital F of infinity equal to 1.
That is true, but I am saying this is, let's say, strictly less than infinity. Think of n as 10. Okay, I'm saying probability of x less than 10 is 1. Sumit, can you tell me?
Sir, I think, sir, this expectation of a minimum of x comma n, and here we are taking that x is less than n. So the minimum value will always be like expectation is what? That is a summation over some x belongs to this AI and probability of x less
Okay,
than
so let's
AI.
write the expectation. Okay, expectation of x n is what? It's integral from 0 to infinity x min n, right?
Yes, sir.
Times dfx of x, right? This is the definition of expected value, right? If you
Yes, sir.
if the density exists, it will be fx of x dx. That's all.
Yes, sir. So after n, this will be 0. This integral, if you make
Now
it this integral,
I can write this as 0 to n.
Yes, 0 to
Okay.
n, then
So 0 to n, what will be x min n? It will be x itself, right?
x itself, sir. Yeah.
Right?
Yes, sir.
dfx of x. And after that, what will be the minimum?
N.
N to infinity, the minimum will be n itself, right?
Yes.
So we have dfx of x. So what is this? This is 0 to n x dfx of x plus, okay, what is this? This is n times, this is
fx infinity 1
probability
minus
of x greater than n, right?
Yes, sir. Yes, sir.
Well, it doesn't matter, I'll make it less than or equal to here, okay? Oh, sorry, I'll keep it as it is, greater than n, okay? Now, what can you say about this now? So, if n equal to, see, n equal to capital N, what happens to this? This is 0 to n x dfx, right? Plus, this is 0, right? Because probability of x greater than or equal to n is 0.
Yes, 0.
That's n is 0, right? So, you get this.
And if you take the limit, it will get the expectation of x only.
Right? This is what we have. Do you agree? Now, I have to basically, instead of min, I have to show that as n goes to infinity, this is equal to expected value of x, right? So now we have, so that is limit n tending to infinity, expected value of x min n is what? 0 to capital N x dfx of x. This is what we have, right? Now we need to show that this is also same as expected value of x. So what is expected value of x? 0 to infinity x dfx of x, right? You agree?
Yes, sir.
Okay. Now what do you do? What do you do? I can write this again. I can split it into 0 to n x dfx of x plus n to infinity x dfx of x, right? You agree?
Yes, sir.
Now I have to do a trick here, right? What is the trick? So n is here, okay, until infinity. What I will do is I will just divide this into small pieces, okay, maybe a piece of size 1, n plus 1, n plus 2, and so on, okay? Do you agree? So I will write this as 0 to n x dfx of x plus, instead of saying n to infinity, I'll do n plus I to, sorry, so n plus I to n plus what? 1 plus I, right? Right? X dfx of x, I have to sum it over all I from 0 to infinity, right? For example, if I put 0, what do I get? I get n to n plus 1. If I put 1, what do I get? N plus 1 to n plus 2, and so on, right? So I'll be integrating over all the entire thing. Is this fine?
Yes, sir.
So again, anyone had question?
So wasn't the proof done already? You've derived the expression for expectation earlier, right? Expectation of
No.
x caret n.
But I haven't shown that that's equal to expected value of x, right, in the limit.
Yeah, but you've already, if you just take limit, you will get the answer, right? You know, there only.
Which limit?
Before the that is line, you've written the first line over here, it's integral 0 to n
This one, right?
x dx. Above that.
Huh? So what do I do?
Yeah, the left hand side of that is expectation of x caret n, right? If you don't assume if n is equal to n, then you just take limit n tending to infinity, the answer is done, right? Because on the right hand side, by definition, that is expectation, right?
But how can you take this n is different from that n, right?
No. Okay, but above the next previous page, above that, yeah, if you don't assume n is equal to capital N, then the answer is done, right?
No, right? So
you just take limit on left and right hand side.
Yeah, true. You are right. I mean, I can take the limit in the sense. So I can take this n tending to infinity. Of course, beyond capital N, this is anyway 0. So, well, the only
We
issue
cannot
is
take it 0 if n not equal to n, capital N.
What is that?
It's 0 if we do not assume that n equal to capital N. I mean, that was our constant, that was equal to 1.
Correct, but if I take this small n to be more than n, this whole product is 0. So as Savan says, this completes the proof, right? So I can just say taking limit as n goes to infinity completes the proof. You are right. Okay. Okay. So anyway, so since we have done this, we will also do the other way. So I can do one more thing here, right? So I equal to 0 to infinity. So in the interval n to n plus I to n plus 1 plus I can just remove. I can substitute for x, right? N plus 1 plus I, because that's an upper limit. So what happens to this? Okay. Now, what can you say about this? What is this actually? I'm integrating the differential of the CDF over an interval from n plus I to n plus I plus 1. So what does that give us?
Probability between x lies between in this range.
Right? So what is the probability of x falling between n plus I and n plus I plus 1?
0.
0, right? So this is 0. Do you agree? Right?
So, this is because we assume that probability of x greater than n equal to less than n equal to 1,
That is
right?
true. That is given.
Okay.
Yeah. So this is 0 and we get this, right? Which is expected value of min of whatever, right? But there is an issue. So this is an upper bound. So what should I do? I should do a lower bound also, right? So if I want to do lower bound, what should I do? I should replace this with n plus I. That's all. Right? So both lower bound and upper bound will give you the same answer. Therefore, this will be the answer, right? Expected value of x. Okay, so essentially you can go in two ways. Show that this is the expected value of min because this is 0, or the easy way, which is what Savan pointed out. I think
actually, sir, may not work because it depends on this probability of the product here. That one also should be 0. So I think you have to show that it is 0. Something.
This too, right?
Yeah, the product you have to show it goes
That
to
is
0.
easy to show, right? So, for example,
no, it may not go if probability does not go at the rate.
it is already 0, right? After n.
Okay, yeah, with that assumption, yeah, it's correct.
Yeah, true. Okay, is this fine? So now you kind of know what kind of questions to expect in your quiz and all that, right? Okay, so okay, anyway, we haven't completed this yet. So if I assume this, that is true, right? If it is bounded, I'm done. So what should I do if it is not bounded? Where is that? This is done now, right? What about general case? How do you solve that? What do you think is the answer? What do you do? Any idea? Anyone? So you can give me you can tell me whether what is the right thing to do here.
Sir, where we have taken a particular capital N, I mean, this capital N is fixed, right?
Yes, it's fixed.
Sir, I mean, for general, we can take any small n and then vary it like something like that.
No, right? So the moment you vary, then the issue is n times this probability should also, as Savan pointed out, this product should also go down to 0 and all that, right? So we don't know.
Sir, can we take the limit inside the integral?
Which integral?
Above, sir. Still above.
Not really. So why?
Sir, actually, that was my question from a homework also, sir. Can limit be taken inside of expectation?
Okay, good question. So we are proving this to prove or to answer your question. Okay. So here I cannot do because I don't know whether I can do it or not. In fact, it turns out you can. That's what this result says, right? This is exactly what you are saying. Good observation, right? So this says you can pull the limit inside. If you pull the limit inside, what is the limit of minimum of x comma n? It's x, right? Do you agree? Min of x comma 10, min of x comma 20, min of x comma 30, and so on, min x comma 1 billion, and so on, min x comma infinity is x, right? Do you agree? Hello?
Yes, sir.
Actually,
Yeah, so essentially you are asking this question of whether I can interchange the limit and expectation in this very, very particular example. Okay, right? So here you cannot just blindly interchange. The question is, can we? And the answer is yes, you can. But that is what we are up to. We are trying to prove that. Yes, somebody had a question.
Yes, sir, you said that the sequence of the minimum of x comma n will be x only, but I think it should be n, sir. No,
Huh?
it should be. Oh,
No, in
we
the
are not
limit.
fixing, yeah, sir. Actually, we are not fixing n here.
Yeah, so
Yes,
in
sir,
the
yeah.
limit it should be x itself, right?
Yeah, sir.
Yeah. Now, can you think of what is it that we have to do in order to prove this? Hey, you guys should think now, right? So it's not just
Sir, we can
one
write
way.
expectation as integration, and in integration we can
Okay.
pull in the limit in the
No,
integration.
that's exactly what we are trying to do, right? So that's the question that we are asking, whether we can pull the limit inside the integration,
Oh, okay.
right? Do you agree? Huh? So suppose I'll also give you this. Suppose, okay, let's look at the other thing. Suppose expected value of x is infinity. Okay. So what can you say about this thing? Is this true? Can we interchange limit and expectation? If the limit is expected value of x is infinity.
Will it depend on the function which we are integrating? It may not be in every case. In maybe some cases where we can take it inside.
No, all that you have to prove now is if this is infinity, the right hand side is also infinity, right? That's what you have to prove. You agree? Right?
Sir, sir, if expected value is infinity, hello.
Yes.
So sir, then we can say that the minimum of x comma n will be n only.
No, right? If expected value of x is
Because
infinity,
expected value,
see, if expected value of x is infinity, for example, what is it? What is it that you can infer? You can say that. So suppose, let me give you an example. You have a random variable which takes value 0 with probability half and infinity with probability half. What is the average?
infinity.
Infinity, right? Right? Yeah. So what is the minimum of x comma
Yes,
n?
sir.
It could be x or it could be infinity. Sorry, it could be x or n, depending on whether it is infinity or 0, right? See, you have to break the problem into
So
pieces.
sir, in that,
right? Okay, fine. Yeah, go
in
ahead.
that case, it will depend on the sequence of x. It will depend on the sequence of x, right?
There is no sequence.
Like,
X is a random variable.
maybe
Right?
that, like, sir, x could be, x is a random variable. So in some case, x could be greater than n also, and in some case, x would be
Correct.
less than n
That's what
also.
I'm asking. On an average, what is the minimum of x comma n? Right? Right? Do you agree?
Yes, yes.
Right? Yeah. So now the question is, what happens if you take expected value of x equal to infinity? Whether you'll get infinity or not. Let's see what is the definition of this. Right? Integral 0 to infinity x, right? dfx
Sir,
of
we
x.
cannot hear you, sir.
Can you hear me now?
Yes, sir. Now we can hear you.
So what is this saying? This is saying, if you look at, for example, some, let's say, n to infinity, x dfx of x is infinity for all n, right? Do you agree? You take any n and integrate, you should get infinity, because the first few cannot give you infinity, right? Do you agree with this?
Yes, sir.
So suppose I give a lower bound on this, right? Something, right? and show that that is also infinity. So essentially what I'm looking at is how the probability is behaving, right, as n goes to infinity or x goes to infinity, right? How is this probability behaving? So can you comment on that? How fast the probability is? Of course the probability may not go down to zero, but as x goes to infinity, but how is it behaving? Okay, let me how do I write this? Let me look at the discrete case. Okay, so what I'm saying is k equal to 0 to infinity, k px of k is infinity. Okay, so what can you say about this? This essentially means that if you take k equal to n to infinity, k px of k, this is also infinity, right, for every k, for every n. Do you agree? Now, when can this happen? Suppose, let's say Px of k is 1 by k cube. This can happen?
No, sir.
Not really, right? Because you'll have 1 by k squared and summation over all k 1 by k squared. Well, just to be, just to avoid this corner case, let's start with 1. Okay. So this cannot happen. What about squared?
Yeah, it will be infinity, sir.
It will be infinity. So essentially it need not be squared, but at least it should be greater than order of 1 by k squared. Do you agree?
Yes, sir.
It means as k goes to infinity, the rate at which probability of k goes down to 0 or remains constant, whatever, it should be more than 1 over k squared behavior. Do you agree?
Yes, sir.
Right? Otherwise, this cannot happen, right? So the probability should be at least 1 by k squared. Now, what can you say about minimum of x comma k, x comma n? Yes. What can you say about that?
You mean the probability of this event or like that?
What can you say about this?
It can take 0 value or 1 value, like is oh no. Yes. So if you fix n for some particular x, it will be less than n, and for some it will be greater than. So for every possible x, it can have either 0 value or 1 value. I mean, it is equal to some another variable y.
Okay. Okay. So now, what is this expected value of x n here? It's summation overall. Let me use k itself, 1 to infinity, right? X. Let me use. Okay, this is k, right? So k minimum n into probability of x taking value k, right? This is what we have, right? Now,
it's kind of indicator function like type of things. Like
exactly, right? So it's an indicator function. I can write this as x less than or equal to n, x greater than or equal to n, right? I can write x as x less than or equal to n, that is x min of n, whatever, right? Okay, what can you say about this? It's the minimum of k and n, right? Till k equal to 1 to n, what do we get? It's k itself, right? Do you agree? From n plus 1 to infinity, what do you get? It's n, right? Do you agree? Now, what can you say about this? Well, I can write it like this: n times probability that x is greater than n plus 1, right? This is what we have, right? Now, as n goes to infinity, what happens to this?
0, sir. Probability should be 0. I mean, x greater than infinity, it should be 0.
No, right? There is n also.
It is multiplied by n. Yeah, I missed that. Yeah.
Yeah, so there is a product, right? What can you say about this?
Sir, second term goes to 0 only if the rate, sir, previously you spoke about. Rate of
That is
probability.
not useful here, right? So if you use this rate, for example, it's 1 by n plus 1 whole squared. So n over n plus 1 whole squared, that anyway goes to 0, right? As n goes to infinity. So you'll get the first term is finite. So it won't help you. Right? Do you agree? Do you agree with this? Okay, so now let's look at this. So, how can I? Okay. Now, what is it that we have to do? So, expected value of x is infinity, but as n goes to infinity, so what will happen to this? What will happen to this? Okay, now, so as
So
n
can you
goes,
just repeat again? What is the problem if it tends to 0?
huh?
If the rate of this probability is appropriately chosen and it goes to 0, what is the problem?
The problem is, of course, okay, that's what. So, okay, man, I want others to answer. So, okay, so I think he almost got it. So now suppose, okay, there are two things that can happen here, right? This can go down to 0 or this can go down to infinity, right? Infinity will be very happy, right? So infinity done, right? As n goes to infinity. But suppose n goes to 0, what happens to the first term? What is limit n tending to infinity summation k equal to 1 to infinity k px of k? What is this? Sorry, k equal to 1 to n. This is nothing but k equal to 1 to infinity k px of k, right? What is this? Do you agree?
Sir,
Huh.
sir, actually we are just, our target is to show that this sum is the infinity, no sir?
Yes.
Yeah, so sir, you have split it into two series, and suppose I'm telling you that if you omit this part, the infinity part, sir, okay, then this expectation of x and n, mean of xn, will greater than equal to this portion, the finite part. And this is the situation that if you give me any number, say whatever the number you will give, I can able to find such a n that will be greater than that number. So this will automatically imply that this expression will be infinity.
No, sorry, I didn't understand.
Actually, sir,
uh,
like sir, we say that something is going to infinity.
Correct.
So suppose there is some series or sequence that is going to infinity. It means that if you give me any number,
that's correct.
yeah, then I can give you a number.
Beyond
that
that
is
stage, it will be
yeah,
greater than all these numbers, all the sequences will be outside of that number.
yeah. Actually, sir, I am just trying to apply the definition of the sequence converging to infinity. So, like
No,
sequence converging to a finite
the issue is x. This converges to x, right?
Yes, sir, this comes, but in this situation, sir, like a expectation of it, you are writing it as sum of the two sequence, and you are saying that if this part, I am omitting this part because I am not fixing this n right now, no, sir.
No, I'm not fixing this, and I can
Exactly,
take
sir.
infinity.
Yeah, any n I can take, no, sir. So suppose I am omitting this right infinity part, so it will give me some finite number.
Correct.
And we can't conclude that this expectation will be finite because will be that number because I just increase this n and then I omit the infinity part. then I will get a number which is greater than that number. Means I can
No, that's what
say
we
that.
are. No, I think you are slightly complicating this a little bit. All that I'm saying is, essentially, I can split this into two sums. One, which is like partial sum for expected value of x. The
Yes,
other
sir.
one, something else, positive, right?
Yes, sir.
So
Yes, sir.
as n goes to infinity, this is by definition expected value of x, which is infinity. Done. Right? That's what Savan implied, right? So is this fine? Okay. So how do you extend that to, for example, non-discrete case?
Hello, sir.
Yes.
Sir, in that equation, the right part,
This one?
n into that thing. When will it become infinity, sir?
It depends, right? For example, let's say px of k is growing at a rate of slightly something like 1 over k squared, let's say. Okay, slightly below 1 over k squared.
Okay.
Right? So essentially, let me think. So when will this be? Yeah, it's a good question. Okay, so this, okay, you are asking whether this will happen or not, right? This question.
Yes, sir.
If infinity will, so okay, so let me think. This is x greater than, it will never happen, right? So we are never not happy with this. It will only be 0 as n goes to infinity. Yeah.
Sir, if
Oh,
P of
wait. So yeah, so this goes to infinity, right? Because see, this is a probability. So as n goes to infinity, this goes to 0, right? Probability. But oh yeah, you are right. So yeah, I take that back. So the product is something that we should look at. So now the question is when this will be infinity, right? This becomes infinity if the probability, this thing, right? It scales as less than 1 by n. Do you agree? For example, if this is 1 by square root n, then it goes to infinity. But if it is n, if it's of the order 1 by n, then this will cancel and you will get a constant, right? On the other hand, if you have 1.1, for example, this goes to 0, right? The right balance, you get infinity if it is something like 1 minus epsilon. Savan, you are saying something.
No, I was saying this only.
Okay. It should be n power 1 minus epsilon, right? Then this product will go down to infinity. Okay, this can happen, right? So for example, if I write the PMF, 0 with probability half, infinity, whatever, dot, infinity with probability half. So for n greater than 1, this is not just n power half, but it's something more than 1 over n power 1 minus epsilon, right? It's a constant actually. Is that okay? Who asked this question? So Praveen?
Yes, sir.
Yeah. Is this okay? So already we are time up. Okay. Yes, Jayant.
Sir, it becomes 0 into infinity, no sir.
Which one?
N into probability of x greater than infinity as n tends to limit
You should not look at it separately. It's a product, right? You should see how the product behaves as n goes to infinity, as n becomes larger and larger.
Okay.
Right? You cannot say, well, n times 1 by n. What happens to this as n goes to infinity? Well, it's 1 already, right? N into n 1 by n is 1. Okay. Is that okay? Fine?
Yes, sir.
Okay. Yeah, I think I'll stop here, but I wanted to complete this. So now think of how to complete this. If so, remember, if x is not discrete, what do? You should somehow convert it into this, right? So one way to convert this is discretize the continuous random variable. Use that, right? What is the next thing to do? So what if x is any random variable and the expected value of x is finite? Now can you interchange the limit and expected value? Okay. So that is something that I wanted to show. So essentially, one can show that if x is x1, x2, etc. is bounded, okay, some b less than infinity, let's say, then expected value of, well, it's okay. Let me state it like this only. So I can write something like this, okay. I can interchange the limit and, oh well, this is less than, okay. So I can interchange the limit and expectation. Okay, what is this called? Anyone? Sumit, do you know what this is?
Yes, sir. Monotone convergence theorem, sir.
Yeah, it's called monotone convergence theorem, right? So this says when can you exchange integral and limits, or expectation and limits. Okay.
Sir,
This
one
is,
thing.
Yes.
So
Yes.
one thing I understand, like I have a small doubt, like sir, what? Sir, x is a random variable. Then what is a sequence of random variable? I mean, like x is following Bernoulli or some distribution. So sequences, like they are different from each other. The sequence.
Yes, you can think of it as, practically you can think of it as different trials. So each trial, okay, so think of it as like this. I have two identical coins. Okay, let's say I have infinite identical coins. Okay. That means the probability of head to occur is, let's say, half in each one of them. Right? I pick the first coin throw, toss, right? The random variable corresponding to that is x1. Second coin, it's x2. Third coin is x3, and so on. So that gives me x1, x2, x3, a sequence of random variables which are IID. Is that okay?
Is it also? It is also, we can say it's like a random process. It becomes like,
yes,
it's not infinitesimal. Yeah.
Yeah, it is a random process, but it's a very simple random process. So nobody studies too much about that under the name of random process or a stochastic process.
And sir, when sir we taking the summation Sn of the first n random variables x1 to xn, what does that mean in that sense? Like x1 will have some 1 value or 0 value, x2 will have some 0 value or 1 value, and then we are adding and dividing, getting the sample mean.
Oh, you are talking about how to get the sample mean, right?
Sn, yes.
Yeah. So you can do one thing. You can take the same first coin, repeat the tossing of that coin 100,000 times, and then compute the average. That is one way of computing the average, right? Or you can do across coins, because all of them are identical, right?
Yes, sir. Yes, sir.
Yeah. So both are same.
Okay.
Both are identical. Okay.
Hello,
so,
sir.
Yes.
Or is it like we have some, let's say x is Gaussian. Then is it like x1 is when we sample for first time, x2 is when we sample for second time, like that?
No, don't. You cannot look at it like that, right? The moment you say sample, that means you are getting a number. That's all.
But
right?
It can be anything, right? It can be anything in the Gaussian PDF, right?
But that's not a random variable, right? Random variable is a function. It's a map. So there, okay, so let me give you an example. So you have a circuits, okay, some whatever. So because of temperature, right? So there'll be some thermal agitation and there'll be some voltage, right? Fluctuations. This fluctuation can be modeled as Gaussian. Okay. Now each time, so this particular fluctuation can be described by the random variable, let's say x1. Okay, which is typically Gaussian with zero mean, sigma 1 squared variance, okay, or sigma squared variance. You have an identical receiver or a circuit, and even here you can model it as Gaussian, but the map is different. So again, sigma squared. Okay. Is that fine? But when you sample it, you will get a number.
Yeah, so actually, sir, here the probability space should be the same for all xi's, no, sir?
Exactly. So the probability distributions are same, but the moment you draw a sample, it's a number. It's no longer a random variable. It's called an instantiation of a random variable. Is that fine? I think who asked this question? Was it Jayant or Praveen? Praveen, right? Yeah. Is this clear?
Sir, I mean, when we will calculate the sample mean, so maybe x1 is taking some value 2.53, x2 is taking some value 3.21, something like that.
Yes,
And
yes.
then we are adding and dividing by n.
Exactly. So law of large number says that when you do this, the sample average asymptotically converges to the true mean almost surely or with probability 1. Right? That's why we do that. You either take the same coin and toss many times and do it, or you can do it across coins. Right?
Okay, sir.
Yeah. In fact, across coins also, each time I toss the coin, I can consider it as an experiment, and I can attach a random variable x1 to it. Second time I toss, I can attach a random variable x to it, and so on. It doesn't matter.
Yes, sir. So
Yeah?
because they're all IIDs, right? Like independent of each other.
Yes, exactly. That's why I can attach the same random variable across or different. It doesn't matter. All of them are IID.
Okay.
Okay. Any other questions? So tomorrow we have a class or no? No, right? Day after tomorrow we have.
Yes, sir.
Right? So
Sir, actually, sir, we have some one or two. I have some one or two doubts from homework also. So can we discuss it that day?
yeah. So Savan, can you look into the homework problems and come prepared on Wednesday?
Yes, sir.
Is that okay? Yeah.
Yes, sir.
Which question you have? So maybe you can tell us quickly.
Sir, question number 3.
No, you cannot say question number 3, man. So I don't have access to homework now. So just briefly describe quickly.
Sir, one is that xn is given like omega over 1 plus n omega cube, and we are asked to find the limit n tending to infinity expectation of xn.
Okay.
Yes, sir. This much information was there only.
Okay. So
now, sir, we have done a theorem over here, no, sir. So if we can show that these xi's are all bounded, then we can interchange the limit.
So maybe you should solve that after next class. Okay. So solve that problem after next class. Okay.
Okay. Sir.
Yeah, Rishabh, you are saying something.
Actually, I blindly do the same thing. I put the limit inside the expectation and I didn't. Yeah.
And now it doesn't matter, right? So the probability distribution of that random variable is irrelevant in the limit, because you can interchange limit and expectation, you get 0. See, even if you say that the probability of so as n goes to infinity, what will happen? So the random variable xn can take only very small values, right? Deterministic, right? Do you agree? So these things doesn't matter. Okay, so I think Sumit, whatever you said was correct. So you can use this result.
Yes.
Here. Jayant, you were about to say something.
Sir, I have one more question. In the problem homework.
Yes.
If xn tends to x with probability and yn tends to y with probability.
In probability,
In probability. So xn into yn tends to xy in probability.
Correct.
Yeah, that question I have doubts.
So I think I discussed briefly with Sumit about that, right, Sumit?
Yes, sir.
I gave a hint also. So maybe just give that hint to Jayant. Okay, I'll give it to everyone now. So xy, how can I write xy? I can write xy as x plus y whole squared minus x minus y whole squared by 4, right? That's the hint.
Okay.
Okay. So all that you have to prove is, for example, if xn converges to x, xn squared converges to x. Okay, and if xn converges to x, yn converges to y, then xn plus yn converges to x plus y. Then you are done. You apply that to this.
Okay, sir.
Yeah, understood, right? Sumit, you are done with that, or?
No, sir. Actually, I didn't get that one, but now I think it will be okay because, sir, this thing I am just a expectation of xn going to x, expectation of x. Sorry, means xn going to x, then xn square will also go to x square. This one, I just stuck on that portion only, sir.
Yeah, so you should think about all possible directions. So
Yes, sir.
oftentimes some people will come up with a very elegant proof. Some other time, you'll come up with a lengthy proof. But that's
Yes.
okay. You have to come up with a proof first.
Yes, sir.
Okay,
Okay.
that's fine. Ayush, are you okay with that?
Yes, sir.
Okay. Yeah. So I thought before getting into random process, I'll just complete this monotone convergence and dominated convergence, these two briefly, and then that will, I think, I'm assuming that I'll be done with that by next class. So the class after that, we will discuss random process, that is Poisson and all that.
Sir?
Yes.
Sir, you mentioned about quiz, sir. So when we can expect the quiz?
So myself and Savan will discuss and get back to you on Wednesday. Okay, in the next class.
Okay.
Okay. I think it's Wednesday, right? So no, tomorrow we don't have a class. So Wednesday. Okay. So Wednesday I'll get back to you. Okay. Yeah. Okay. If there are no questions, then I'll stop here. Okay. Questions? Okay. Okay, then we'll meet on Wednesday. Thank you.